Hello students, today we are going to start with a new topic called virtual memory. Linux virtual memory. Linux shares many of the characteristics of the memory management scheme of other Unix implementation, but it has its own unique features. Overall, the Linux memory management scheme is quite complex. In this section, we will give a brief overview of the two main aspects of Linux memory management: process virtual memory and kernel memory allocation. Virtual memory addressing. Linux makes use of a three-level page table structure consisting of the following types of table. Each individual table is the size of one page. First type, page directory. An active process has a single page directory that is the size of one page. Each entry in the page directory points to one page of the page middle directory. This page directory must be in the main memory for an active process. So basically it says that Linux makes use of a three-page level table structure, and page memory is just like, assume that it's a one page of a book. Page middle directory. The page middle directory may span multiple pages. Each entry in the page middle directory points to one page in the page table. Page table. The page table may also span multiple pages. Each page table entry refers to one virtual page of the process. To use this three-level page table structure, a virtual address in Linux is viewed as consisting of four fields, which will be seen in the next slide. The leftmost, that is the most significant field, is used as an index into the page directory. Just like in every first page of the book, there is an index page. The next field serves as an index into the page middle directory. So basically, every page directory has its own index. The third field serves as an index into the page table. The fourth field gives the offset within the selected page of memory. So you can see that there is a chain of instructions from first page to second page to third page and to the main page. The Linux page table structure is platform independent and was designed to accommodate the 64-bit alpha processor, which provides hardware support for three levels of paging. With 64-bit addresses, the use of only two levels of page on the alpha would result in very large page tables and directories. The 32-bit Pentium/86 architecture has a two-level hardware paging mechanism. The Linux software accommodates the two-level scheme by defining the size of the page middle directory as 1. So the page middle directory is the main part of the virtual memory, and it determines the size of it. Note that all references to an extra level of indirection are optimized away at compile time, not the run time. Therefore, there is no performance overhead for using generic 3-level design on platforms which support only 2-level in hardware. In simple words, a person cannot install Windows 10 in a Windows XP capable computer. We'll see to the picture regarding the page table in the next. Page allocation. Page allocation is important because it helps in enhancing the efficiency of reading in and writing out pages to and from main memory. Linux defines a mechanism for dealing with contiguous blocks of pages mapped into contiguous blocks of page frames. For this purpose, the buddy system is used. The kernel maintains a list of contiguous pages frame groups of fixed size. A group may consist of 1, 2, 4, 8, 16 or 32 page frames. As you can see in the picture below, virtual address is divided into 4 sectors: global directory, middle directory, page table, and offset. So a register, if it wants to go to page directory, it goes via global directory. Then from there, if it needs to go to middle directory, it goes via middle directory. If it wants to go to page table, it connects via page table. And if it wants to come to the main physical memory of the page frame, it comes via offset. So the figure is the address translation in Linux virtual memory scheme. Kernel memory allocation. The Linux kernel memory capability manages physical main memory page frames. Its primary function is to allocate and delocate frames from particular users. Possible owner of a frame includes user space process. That is, the frame is part of the virtual memory of a process that is currently resident in a real memory. Dynamically allocated kernel data, static kernel data, and the page cache. So basically the first paragraph tells about the function of kernel memory. The foundation of kernel memory allocation for Linux is the page allocation mechanism used for user virtual memory management. As in the virtual memory scheme, a buddy algorithm is used so that memory for the kernel can be allocated and deallocated in units of one or more pages. So basically, as you have seen in the previous diagram, that how the register is shifted from page to page. So it is how the kernel helps in shifting the units from one page to another page. Because the minimum amount of memory can be allocated in this fashion is one page. The page allocator alone would be insufficient because the kernel requires small short-term memory chunks in odd sizes. To accommodate these small chunks, Linux uses a scheme known as slab allocation within an allocated page. It's just like a book having different page numbers in simple terms. On a Pentium/86 machine, maybe it's the Intel processor which they meant to say, the page size is 4 kilobytes and the chunks within a page may be allocated of sizes 32, 64, 128, 252, 508, 2040 and 4080 bytes. So as per the size increases, so the performance also may increase. The slab allocator is relatively complex and is not examined in detail here. A good description can be found in Dbce-Goa, which you will learn in, if you are interested, you can research through it. In essence, Linux maintains a set of linked lists, one for each size of chunks. Chunks may be split and aggregated in a manner similar to the buddy algorithm and moved between lists accordingly. So this is all about kernel memory allocation system.
From this topic, virtual memory, we have learned that a virtual memory management scheme requires both hardware and software support. The processor does the work of providing hardware support. This support includes dynamic translation of virtual address to physical address and the generation of an interrupt when a referenced page or segment is not in main memory. Such an interrupt triggers the memory management software in the operating system. A number of design issues relate to operating system supports for memory management. So the first one is fetch policy. Its process pages can be brought in on demand or a pre-paging policy can be used, where a number of pages are brought together at once, clustering the input activity. Next one is placement policy. With a pure segmentation system, an incoming segment must be fit into an available space in memory. Next one is replacement policy. When memory is full, a decision must be made as to which page or pages are to be replaced. Now let us discuss about resident set management. The operating system must decide how much main memory to allocate to a particular process when that process is swept in. This can be a static allocation made at process creation time, or it can change dynamically. Next is the cleaning policy. Modified process page can be written out at the time of replacement, or a pre-cleaning policy can be used which clusters the output activity by writing out a number of pages at once. And last is load control. Load control is concerned with determining the number of processes that will be resident in main memory at any given time.
This is our reference for this topic. Thank you and have a great day.